everybody. Let's give this problem a try. It looks like a long problem, so you can pause at any time when you need to. Let's try using the method of joints for this one. Okay, now let me just walk you through my thinking here. If let's go through this alphabetically. Joint A here has two of these members attached, so there would be two unknown axial forces. Okay, so two unknowns. Joint B has three axial forces, so three unknowns. Joint C has three axial forces plus this roller support, so that's four unknowns. Joint D has the two axial forces and then a pin, which is a two-dimensional reaction. So if I decompose it, it could be like this, for example, four unknowns, right? So joint A, two unknowns, joint B, three, joint C, four, joint D, four. So I think the clever approach would be to start at joint A, and then we could solve for both unknowns. So then we would already know this one, which is the same as this one. So when you get to joint B, there would be these two unknowns, right? And then when you get to joint C, let me clean this up a little bit. When you get to joint C, you would already know this one from solving joint A, and you would already know this one from solving joint B, which leaves you with two unknowns, that and that. And then at joint D, we would already know this from joint B, this from joint C, and then we would know all of the axial forces at this point. We can still write two more equations to solve for the reactions at that pin, and then we would know everything for this structure. Okay, so this particular problem is just asking for the axial forces in the members. So, all right, let's give it a try. So starting at joint A, right, it looks like I'm drawing the axial forces in tension. So that means for member AB and then for member AC. So if I draw the arrow in tension, if the value is positive, that means it was in tension. But then if the value is negative, that means the axial force is in compression. Okay, and then there's the load here, 1 kilonewton. All right, so if I pick a, all right, let's pick coordinate axes. How about, I'll pick my origin here. Kind of crooked, right? So like this. All right, so those are my axes. So if I sum forces in the x direction, it would be the x component of TAB. So let me just write it generically for now. So the x component plus the x component of AC. That's it, right? Because this doesn't have an x component. And in the y direction, the y component of this, so TAB y component plus TAC y component, and then this, minus 1 kilonewton equals 0. And I'm writing it generically because this is a variable. So I am leaving it generic for now, because then I'm just going to plug in this value first for everything and then solve. And then when I finish everything, I'm going to go back to the beginning and plug in this value here. Okay. So just looking at it, we have, well, let's figure out the x and y components of these vectors first. Okay, starting with vector AB. Okay, so this vector has a magnitude. This magnitude is unknown. We don't know the number. But the direction is a unit vector from A to B. A unit vector from here to here, like this. We can get that. Well, let's see. We need to do a little bit of... Where is A? Okay, so A is 1.8 in the x direction and 0.7 in the y direction. Where is B? B is 0.6 meters in the x direction and h plus 0.4 in the y direction. Okay, and C is in the x direction 0.6, and then the y direction 0, and then point D is in the x direction 0, and the y direction 0.4. Okay, so I got all 4 points. So if I want to go from A to B to get this unit vector here, it's where you end minus where you start. Right, so in the x direction, 0.6 minus 1.8. Unknown magnitude. Okay, so unit vector. 0.6 minus 1.8, so that's negative 1.2. That's I. And then in the y direction, h plus 0.4 minus 0.7, which is h, h minus 0.3 j. Okay, and then the magnitude is this squared plus this squared squared. 1.2 squared, h minus 0.3 squared. Okay, so then for part A, just plug in 0.1 over here and over here. Okay, so then you're going to have something I, something j, and depends which value, right? I would do part A first, right? And then do part B later. Okay, and then for vector AC, unknown magnitude, and then the unit vector from A to C is, okay, A is here, C is here. So where you end minus where you start, right? So 0.6 minus 1.8. So negative 1.2. And then in y direction, 0 minus 0.7. So negative 0.7. Okay, and then the magnitude is this squared plus this squared, square root. 0.2 squared, 0.7 squared. Right, so then you have something I, something j. Okay, let's see. So I'll just kind of point out what to do here. Okay, see this equation? The x component of AB is this. It is negative 1.2 over this times TAB. Right, so it's negative 1.2 over this h minus 0.3 squared TAB. Okay, now the x component of AC is here, right? It's negative 1.2 over 1.2 squared plus 0.7 squared TA. Oops. This should be a C. Sorry about that. C. Right, because that's C. TAC. We're doing this equation, right? Equals 0. Okay, so this is this. Now, this one. The y component of AB is here. So, let me, just to keep track, right? This is the x component. This is the y component. Okay, so the y component is this. H minus 0.3 over that thing. TAB plus the y component of this, which is actually a negative, so negative 0.7 over that TAC minus 1 kilonewton equals 0. So now take a look at this. We have two equations, two unknowns. Right? So just pick one, right? Let's say solve this for TAC. TAC is minus 1.2 over this. TAB divided by this. So things start actually canceling, like this, these cancel and such, right? So then now you take this expression and you plug it in here, right? So then you just rewrite this whole equation with all of this here. Okay, so when you work it out, I kind of skipped a little bit of plugging in numbers for now, but when you try it yourself, you should all just plug in 0.1 over here already. So this whole thing will just be a number, right? I'm kind of just, I didn't want to use the calculator at this point, so. Okay, actually, maybe I should. I'm just gonna, how about I pause? I'll punch these numbers in the calculator. I shouldn't have erased what I just had there. Okay, so, oh, it's kind of messy anyway, but, right, so I'm going to plug all this in here, simplify, and then I'll get a value. So let me pause and I'll just punch in the numbers. Okay, so, well, if I punched in the numbers correctly. In any case, you have two equations, two unknowns, which means you can solve for both. So this is in tension, this is in compression. But then now, actually, let me copy this. So when we go to the next joint, okay, hold on. Okay, so let's say now we go to joint B. So the free body diagram at joint B looks like this. Okay, so member BD, member BC, member AB. We already have this value, right? Here, it's known, which means we only have two unknowns. Right, so we have two unknowns here and here. So let's write two equations for those two unknowns. So in the x direction, we got the x component of this. I'm just going to write that generically because, again, we have this variable here. I wouldn't normally do that. I think normally I would just get an angle like that since this is two-dimensional. But because we're dealing with this variable here, I think it's less work if we write it generically and then just plug in values twice. Okay, so the x component of this plus the x component of this. It's fair to say that's vertical, right? So there is no x component of this. And so it's just the x component of this equals 0. Okay, and now in the y direction, the y component of this plus the y component of this, which is the entire thing, plus the y component of this, AB, right? Which we know the answer already. Okay, let's see. So for BC, that thing is just vertical. So let me just write that, right? So vector BC is the magnitude, and it's just going in the negative j direction, right? So I'll just write negative j. Okay, that's it. There's no y component. For vector BD, we need to do a little bit of work, right? So we don't know the magnitude, but the direction is a unit vector from B to D. What is the unit vector from B to D? Where we end minus where we start, right? So in the x direction, 0 minus 0.6, so negative 0.6. And then in the y direction, 0.4 minus quantity h plus 0.4. Oh, so that's nice because these cancel, right? So it's actually just negative h. Okay, and then the magnitude, 0.6 squared plus h squared. Okay, so then, let's see. So we can start plugging in values for here. Okay, so the first equation, this one, some forces in x. Okay, so the x component of BD is right here, negative 0.6 over 0.6 squared plus h squared TBD, and then the x component of AB, which we know, hold on, let me grab it. Okay, where did I write it? Okay, I'm gonna copy this. Okay, so it's just this part of it right here. Okay, I'm just copying and pasting stuff. So let me just get rid of this. Okay. And so this is this part right here. And then the magnitude was 2.43. Okay, now if you look at it, there's actually only one unknown here, right? So that's nice. Okay, now y component. We're doing this equation right here. Okay, so the y component of BD, which is right here, negative h over 0.6 squared plus h squared t b d. Okay, now we're over here. The y component of BC, which is actually just this, negative t bc, and then the y component of AB, which is just this part right here. Okay, so let me just copy and paste it. Oops, no, I just cut it. There we go. And let me get rid of the stuff we don't need. This x component part. Okay, there we go. So plus this, and then the magnitude 2.43. Okay, so actually let me highlight the unknowns. Okay, so we have these two equations, two unknowns. And right, solve this one first. For BD, there's only one unknown. Take that value, plug it in here, and then solve for BC. Okay, can I leave you to do that? Solve this one first, plug that number in here, and then solve for this one next. Okay, and then let's see. I guess maybe I should write the numbers. Okay, let me pause. All right, the numbers are a little bit surprising. I got the same magnitude as AB, and then this I got 0. So, all right, sounds good. This is in tension, and that's 0. Okay, so now okay, hold on. Let me get this again. Okay, now let's move on to joint C. So joint C looks like okay, so over here, right? This is member AC, this is member BC, this is member CD, and then we have this roller support, which only has a Y component. Okay, but the thing is, we have this answer already somewhere. Minus 2.78. Minus 2.78. Okay, so actually, this is in compression. The arrow is actually going this way, 2.78, or you can draw it going out with a minus sign. And this answer, we just solved that, right? Oh, it's 0. Interesting. Okay, so that's 0. No complaints there if something is 0. This is 0, which means we only have 2 unknowns, and we can definitely write 2 equations. Okay, so the x component of this plus the x component of this, which is 0, plus the x component of this, which is 0, plus the x component of this, which we already know. Okay, now y direction. The y component of this, TCD, y component. The y component of this, which is 0. The y component of that, which is the whole thing. And then the y component of AC, which we already know. Okay, let's see. I think we need an expression. Hold on. Yeah, we didn't write an expression for this vector yet, right? So let's do that right now. So vector CD is some unknown magnitude, and then the direction is a unit vector from C to D, no problem. From C to D is here to here. So where we end minus where we start. Okay, so in the x direction, 0 minus 0.6, negative 0.6. And then in the y direction, 0.4 minus 0. So plus 0.4. Okay, and then the magnitude, 0.6 squared plus 0.4 squared. Okay, so now let's plug these values into these 2 equations. So in the x direction, the x component of CD, right here, negative 0.6 over 0.6 squared plus 0.4 squared TCD, plus the x component of AC, which, let me just, where is it? Here? This is, I'm going to copy and paste that, right, because this is for AC. Okay, only the x component. So let me get rid of the stuff we don't need here. So I'm going to get rid of the y component. There we go. Okay, so the x component of AC is this times TAC, which we know, negative 2.78. Negative 2.78 equals 0. Okay, so this only has one unknown, so that's nice. Okay, now this equation, the y components. Let me move this. I'm going to use it in a second. Okay, in the y direction, the y component of CD, which is right here, 0.4 over 0.6 squared plus 0.4 squared TCD plus CY plus the y component of AC, which is just this part right here, negative 0.7 over 1.2 squared plus 0.7 squared TAC, which we know is negative 2.78 equals 0. Okay, and then this equation has two unknowns, right? Okay, so then solve this one first for t, c, d, right? Get the number, and then plug it in here, and then solve for, oh, actually, we don't care about that, right? Okay, so then just solve this one for t, c, d, and then we're done. Okay, I might as well just do that, right? Since I did all the others. Okay, so there we go. This is negative, so this is actually, for, you would say, for member CD, the axial force is 2.88 kilonewtons compression, right? So, okay, so I think we got everything, right? We got all of them. Okay, but then this is a long problem, right? Go back to the very beginning, and then now you see you have to replace h with 0.5. So right from the beginning again, right? So joint A, plug in 0.5 over here and over here. Oh, actually, this stays the same. Okay, so that's not so bad. So vector AB changes, but then AC actually doesn't, so it's not so bad. So you don't have to change a lot of stuff. So AB, oh no, it's going to affect everything. Okay, yeah, so, right, this will change the numbers here, and then just go through the whole thing again. Same exact process though, just the numbers you punch in the calculator will be different. Okay, so, sorry, long problem, right? But give it a try. If you have questions, let me know. Other than that, I'll see you on the next video.